and it's going to be the new topic for this week and part of next week, I suppose. It's called rigid body kinematics. So far, we've looked at particles, right? And particle kinematics. And by kinematics, we mean basically geometry and calculus. And particle kinetics, by which we mean basically Newton's laws and other related things. So let me just say very broad, within quotes, F equals ma, relation between forces and motion. Okay, so that's what we've looked at, particles. And of course, particles are objects that are characterized by only position. So that's a particle. But for a lot of problems, we might care about both the position and the orientation of an object. So, and the simplest kind of an object that for which you can meaningfully talk about position as well as orientation is called a rigid body. So it's the simplest object. For which both position and orientation matter, right? So you can imagine this object. It might be moving in some manner, but it might also be rotating in some manner, right? So this is, I suppose this point has some linear velocity, but the whole thing might be rotating and changing orientation, right? So any questions about that? So this you would call translation. So let me just say position could change. And the orientation, my handwriting for some reason is not so great and I'm doing things live, but orientation could change. Okay, so that's a rigid body. It's the simplest object for which both position and orientation could matter. And we contrast rigid body with a deformable body. What do we mean by a deformable body versus a rigid body? Basically, deformable body could change not just position and orientation, but in addition, it could also change shape, can change position, orientation, and then shape. And when we say that shape changes, that's what we mean by saying the body deforms. But rigid body does not change shape. Right, so does not change shape. Okay. Any questions about that? So sort of central concept, we already know about linear velocities. Like you have a point, it can have some velocity. The next sort of thing that we want to define is the notion of an angular velocity for a rigid body. okay, angular velocity for a rigid body. And here's how we define this. Imagine a rigid body, an object, which basically cannot change shape. And we have 2 points on this object. We have point A and point B. And it could be any 2 points, right? So consider, well, okay, angular velocity for a rigid body, and then we are going to do this in 2D. We are really only going to be doing 2D kinematics and dynamics for rigid bodies, and 3D kinematics is, I guess, a subject for a different course, um, which I guess I also sometimes teach at the graduate level, and also teach, take a intermediate dynamics course, which is offered in the mechanical engineering department, if you're interested in that as well. But in any case, so we are going to consider angular velocity of a rigid body in 2D. So the rigid body is perhaps spinning, but restricted to this plane. It's not spinning in 3 dimensions, but it's spinning in 2 dimensions, or moving in 2 dimensions. So consider any 2 points A and B, on the rigid body. Okay, and then you draw a line joining those 2 points. So you draw a line joining those 2 points, and then we consider the x-axis, let's say, and we consider the angle that this line makes with the x-axis. Let's call that theta. Okay, so consider, well, we can say theta is angle made by line AB with some fixed axis, say x-axis. It doesn't matter what fixed axis is, but let's say x-axis. Okay, some fixed axis in the plane. It needs to be in the plane, I suppose. Okay, so theta is that angle. We took any 2 points, it makes some angle with some fixed axis. And then d theta by dt is basically called angular velocity. This is a scalar of the rigid body. Often denoted by omega, and the vector angular velocity let me say angular velocity vector omega with a bar. So when you use these variables, you do want to make sure that you use a scalar notation for scalars, a vector notation for vectors, and you don't want to mix them. So angular velocity vector, which I'm denoting with the bar here, is basically omega, the scalar, times the k unit vector. Okay, so it's spinning in this plane. It's sort of changing orientation. This angle theta is changing, and the rate of change of this angle is defined is the scalar omega, and that omega multiplied by the k vector, which is perpendicular to this plane, is called the angular velocity vector. Okay. So I used this word super carefully. I said angular velocity of the rigid body. I didn't say angular velocity of AB. I said angular velocity of the rigid body. Okay. And this is an important sort of difference, and it's a little subtle. We started out by saying consider any 2 points A and B on the rigid body. And this omega is defined as the rate of change of this angle made by AB, where A and B could be any 2 points, right? What if we had picked some other 2 points? Would the angular velocity be different? So if you pick some other 2 points, so let's say this is A and B, and let's say we pick some other 2 points, C, let me just pick some other points which don't hopefully make the same angle. C and D or something. Let me say A and B are like this. So this is AB and this is CD, okay? AB makes angle theta with the x-axis. CD will make some other angle with the x-axis. But the rate of change of that angle that CD makes with the x-axis will be exactly the same as the rate of change of the angle that AB makes. Why is that? So if you say this is theta, and if you, let's say, make this alpha or something, or maybe alpha is the wrong word. Let's say beta, because alpha we're going to use for actually some other variable. A few people have answered in the chat window. All right, so the correct answer is that the body is rigid. And because the body is rigid, the angle between AB and CD is some constant. So basically, if you say theta minus beta is basically some constant. Because the object is rigid, the relative position and orientation of AB and CD is not going to change. Like, even though AB's position and orientation will change, CD's position and orientation will change, because the object is rigid and not changing shape, the angle between them will remain the same. So theta minus beta will remain same because rigid body. And this means that if you differentiate both sides, d theta by dt minus d beta by dt equal to 0. Okay, so our theta dot equals beta dot. So what that means is that, well, omega, the angular velocity vector of the rigid body, is equal to, well, you can say it's theta dot k, or you can say it's beta dot k. It's all going to be the same vector because, well, this derivative does not depend on which 2 points you pick. So when we say the object has an angular velocity, we're saying the object has an angular velocity, not not a particular like line on that object or anything like that. It's a property of the object. Okay, so that's super important. So angular velocity omega is a property of the object.
Professor, will you remove your chat window? It's blocking your handwriting.
Oh, I see. Sorry. Thank you for letting me know. Cool. Okay. Okay. Angular velocity omega is a property of the object as a whole. Okay, I guess period, basically. It does not depend on A, B, C, D, whatever. Does not depend on choice. Okay, so that's a principle. So it's a property of the object as a whole. We don't say angular velocity of point B or point A or point C. It's the angular velocity of the object. Okay, super important concept, easy to forget. Okay, So that's one. And then there's angular acceleration. And another sort of related thing is that it need not be rotating about a point or anything like that. All that matters for angular velocity to be defined is that it change orientation. This angle changes, right? It could be sort of going in some direction while also changing orientation. It need not be rotating about a point or anything. All that matters is that these angles change, which will change if the orientation changes, right? So we don't say angular velocity about a point. We just say angular velocity of the object, period, right? So let me just say that. Also, we do not have to say, we do not and do not have to say, have to say um, angular velocity about a point, because we didn't like really assume that it's rotating about a point or anything like that to define this this concept, right? Um, this object is changing orientation, these angles are changing, and it's just a function of how those angles change. Okay, um, so that's the second point. Um, cool. Okay. The next concept is angular acceleration. Usually denoted by alpha. This is if you're using the vector, you use alpha with the bar, and then alpha scalar would be the scalar component, I guess. Okay. Um, and this is just defined as d omega by dt, or it's defined as, well, d omega scalar by dt k, which is the same as alpha k, right? So your alpha scalar is d omega scalar by dt, and your alpha vector is d omega vector by dt, okay? Any questions about this? So that's angular acceleration. This is just basically, let me just say it's equal to d square theta by dt square, or theta double dot, sort of the natural thing. Again, it's a property of the whole body, not like it's not angular acceleration about a particular point, off 2 points, anything. It's a property of the rigid body's motion as a whole. Okay, so that's angular acceleration. So those are the main definitions. Now we'll write down a couple of formulas, which I'm not going to derive particularly. We'll give some intuition for it. So the main two definitions are new objects are angular velocity and angular acceleration. And the two big formulas, kinematics formulas, relations in rigid body kinematics. So let me write both those things down first. So imagine you have a rigid body and you happen to have 2 points on the rigid body, A and B. And let's say point A has some velocity A and point B has some velocity B, okay? Sounds good, okay. And the whole object has angular velocity omega equals, omega vector equals omega times, omega scalar times k. The first relationship basically is a relation between velocities of A and B. So relation one relates VA and VB for any 2 points, A and B, for any two A and B on a single rigid body, on the same rigid body. Okay. Okay, so then this is the relation. I'm just going to write it down. So it says VA equals VB plus omega cross, this is a cross product, RA with respect to B. This is the, or another way of saying this, this is equivalent to VA minus VB, both vectors, not scalars, right? So this is a vector relationship, VA minus VB is going to be equal to omega cross. When we say R, this is R, right? QRST, that R. Let's say R. So this is basically RA minus RB, if you want to write it like that. Or you can equivalently write it as V of A with respect to B equals omega cross RA with respect to B. So I guess these are all equivalent ways of writing the same thing. We'll probably use this most common version. We will use this version, I guess. So let me call this equation number one. So it says, if you have 2 points on the rigid body, then they can have a relative velocity. Like A can move relative to B, but it's actually, we will see in a minute that if you actually work this out, well, what can be the nature of the relative velocity between A and B? Can sort of intuitively think of what is the nature of the relative velocity between A and B? If A and B are on a rigid body. Yeah, so Jake, what Jake said on the chat window is basically right, which is that, well, okay, if A and B were just general points that were not on a rigid body, then they could move in any old direction. A could move in some direction, B could move in a completely different direction, and there's no real constraint on the motion of A and B. But on the other hand, because they are on the rigid body, in other words, well, what does it mean to say that they're on the rigid body? It means that the distance between A and B cannot change, right? So the distance between A and B cannot change, but while maintaining the distance, B can rotate about A or A can rotate about B. So the only kind of motion, relative motion between A and B can be a kind of a rotation of A with respect to B or B with respect to A. And that will basically not change the distance between A and B. The reason you cannot change the distance between A and B is because this is a rigid body, okay? So, so this formula actually has that geometric interpretation. Omega is perpendicular to the plane, or A with respect to B is this vector. And when you say omega cross RA with respect to B, when you do a cross product between two vectors, it's going to be perpendicular to both these vectors. So this relative velocity is going to be perpendicular to this vector and the vertical vector out of plane. So it's basically going to be perpendicular to this vector, right? So let me just write that down. Because we are, well, not we, A and B are on a rigid body, the only relative motion between A and B um, can be a rotation of one relative, well, one about the other or something like that, crudely speaking. So, and basically your equation that we have, VA with respect to B, is omega across RA with respect to B. And if you have AB, this is basically RA with respect to B. This is A, this is B. And your omega cross omega equals omega K, which is perpendicular to the plane. So VA with respect to B is necessarily going to be like perpendicular like this. As if A was rotating about B or something like that, okay? Okay, so I guess you recall cross products. If you say C equals A cross B, implies C is perpendicular to A and B, okay? So that's the principle of cross product, I guess. Okay, so that's basically all there is here. Well, it's good to remember this sort of intuition about what this relative velocity means, but ultimately, all that matters, I guess, for the homework problems and the exam problems is this formula, which tells you, well, if you know the velocity of B, and if you knew the angular velocity, you can compute the velocity of A, or vice versa. That's basically what this formula tells you. Okay. If you know the velocity of B and you knew the angular velocity, the velocity of A is just velocity of B plus this term, which tells us relative to B, sort of how A is rotating, I suppose. Okay, that's the meaning of that. So that's the end of that relationship. We'll use this in a problem in a minute. And then the next relation 2, has to do with accelerations of A and B. So if you have 2 points, A and B on the rigid body, A, B, and let's say, again, we have some acceleration of point B and some acceleration of point A, and we have some omega of the rigid body, and we also have alpha, angular acceleration of the rigid body, okay? All these are given. Um, And the acceleration formula is this: acceleration of A equals acceleration of B plus, there's two terms now, two more terms, quite analogous to how basically the relation that we are going to write down is the derivative of this relationship. You differentiate the whole thing. Like if you want to know how to derive this, this will become acceleration of A, this will become acceleration of B. And then this, because there's two terms, when you differentiate it with respect to time, gives you, well, because the product of two objects, you have to do chain rule or product rule, and you get sort of two terms when you differentiate it. One is like alpha cross RA with respect to B. Another, it turns out, is something, well, let me just write down what it is. So it's alpha cross R A with respect to B plus something like this, omega cross R A with respect to B. Okay, just to be very clear, all these things are cross products, right? So these are all vector cross products. In case you're looking at this notes again at some point. So all these are vector cross products. They're not just simple multiplications, they're all vector cross products. Any questions about this? So it turns out just like this omega cross R had a simple geometric relationship, which is the rotation of A with respect to B, these terms also have a simple geometric relationship, sort of going back to what we did early in the course. So let me write B here and then A here. And R, this is R of A with respect to B. Okay. And your alpha, so if you have alpha in sort of this direction, then alpha cross RA with respect to B is going to be in this direction. I'm not writing this very well. Let me draw a bigger version of this. So that's RA with respect to B. And basically, one of the vectors, this is going to be alpha cross RA with respect to B, which is going to be perpendicular. Well, alpha is perpendicular to the plane. So when you go alpha cross RAB, the vector is going to be perpendicular to this vector, as well as perpendicular to, well, the K vector. So that's going to be in this direction. It's going to be some vector in this plane that is perpendicular to this thing. So it's basically something like this, right? It could, of course, be in this direction as well. But by the sign convention, I guess, by default, we would put it in this sort of clockwise manner. And then this term, you can also reason how this is going to be. Sort of using cross products, do you want to reason like the direction that this vector is going to be in? So what is the direction of this vector? Omega cross R. We just saw that omega cross R is perpendicular to this RA with respect to B. So omega cross R is going to be in this direction. And this is omega cross R. So you take, well, you start with RA with respect to B, and then take the cross product with respect to omega. You get a vector here. That's this thing. And then you do omega cross R. That's going to be perpendicular to this vector, which is going to be, well, either this or this direction. So it turns out that this term is actually like this by default. Again, from the purposes of solving a problem, this geometric interpretation is not essential, but it's helpful to understand like where are these weird expressions coming from. And really, well, this has a name that you're all familiar with. Wouldn't this be RB with respect to A? That's right. I should have said, okay, the picture is slightly wrong. I want to say this is, sorry. I guess this is B, this is A, okay? Sorry. Cool, thank you. I guess I have the chat window open just now. So this is the fix that I just made. I interchanged B and A. Yes, this is, this vector is going to be the R A with respect to B. Okay, so when we say RA with respect to B, it's the vector B to A. It's the bottom thing to the top thing, is what we mean. Okay, that was a typo on my end. Any questions? So this term has a name that you're all familiar with. It's basically the centripetal acceleration term. If you imagine A rotating about B, this is like the centripetal term of acceleration. This is the sort of tangential term or whatever. This is a normal term. This is a tangential term, centripetal term, and the sort of theta term, and so on. Okay. So omega cross R A with respect to B is centripetal acceleration of A with respect to B. WRT means with respect to, just to be clear. Okay. Okay, so that's a geometric interpretation. If there are 2 points on a rigid body, if there are 2 points on a rigid body, they can have velocities relative to each other, and that has the like basically the relative velocity can only be perpendicular to the line joining AB, and they can have accelerations relative to each other. The acceleration can have a centripetal term and like a perpendicular to the sort of line joining AB term. And I guess that's it. So that's the geometric interpretation, but ultimately you'll be using this formula. So just because A and B are in a rigid body does not mean that there can be no acceleration along this direction. There can be an acceleration. That acceleration will not change the distance because the velocity in this direction will always be 0, the relative velocity. But this acceleration basically changes the direction of this vector, like centripetal acceleration usually does. Okay, so that's the high level. But ultimately, we're just going to use this formula and this formula. So let's see. Let's write down a problem that sort of go through the motions of using these formulas. So given some object, A and B on it, given VA equals, well, let's say 3 I plus 4J in some direction. Omega equals, let's say 5K. Determine, well, and then the position of A is, let's say, momentarily at 0, 5, and in Cartesian. And the position of B is, let's say, 3,7 in Cartesian. Determine VB. Well, it's kind of a straightforward formula application problem where you say, well, we wrote the expression for VA in terms of VB, but now you can write equally VB is a function of VA plus omega cross R B with respect to A. Okay, so RB with respect to A is basically going to be RB minus RA. So we have 3i. So this is basically RB, the position vector of B. So we have 3i plus 7j minus 0i plus 5j. So 3 minus 0 is 3i. 7 minus 5 is 2j. So that's our B with respect to A. And then now we can plug everything in. We already have been given VA. We just computed this. We know omega, so let's do that. VA is 3 plus 4j, or 3i plus 4j. That's VA. So we are using this formula here, plus omega is 5k. And then you do cross. There's a cross product, 3i plus 2j. Let's quickly do this cross product and then we'll end today's lecture. And then we will do the acceleration. We'll do an example with the acceleration version of this formula. And then we will quickly start studying more complex mechanisms, kinematic mechanisms using these formulas. Right? So it turns out these formulas underlie the kinematics of sort of important machines that have, I guess, well, important machines, I guess. So we'll do that next time. But for now, we'll just do this cross product and leave it at that. How do you do cross products? So you want to review cross products. How do people like to do cross products?
Tables and then take the determinant.
Yeah, so there's a determinant way, which is certainly correct and will work.
A table.
A table.
Yeah.
What table is it?
Like you put the I, J, and K on top, and then you put the vectors corresponding to those coordinates around the bottom, and then like for the first, then you take the first row and first column, you get rid of those. Well, you imagine those numbers don't exist, then you
I see.
cross multiply. You cross multiply. Yeah, it's hard to explain, but
No, I get it. Yeah, I think I get the, yeah. Cool, awesome. Cool. But yeah, what you were describing is basically correct as well. But yeah, so you can do the determinant. So to do cross products, excuse me. So you can do 3i plus 4j plus you can set up this determinant I, j, k, and 0, 0, 5, 3, 2, 0, or something like that. And you can do this where this is just 3i plus 4j. And then you go I times, you do 0 times 0 minus 2 times 5. So it's just 0 minus 10, hopefully. And then you go minus j. This is how determinants work. So you have a plus and then a minus and then a plus again. Minus j, this times this minus this times this. So 0 times 0 minus 3 times 5. Well, I guess just to be clear, this is 5 times 2, 2 times 5 or something. And then you have a k, k times this, and this times this. That's just a 0 times 0, whatever, right? So whole bunch of zeros. So that should work. 3i, hopefully I did that right. So that's going to be a minus 10 I, and then this is going to be a minus 15 plus minus j plus 15, I guess, plus 15j, and then 0k. Hopefully that we got that right. So we will have equal to 3 minus 10 is minus 7i, 4 plus 15 is plus 19j. Okay, so that's, I suppose that is velocity of b. You can check if my arithmetic is right. Okay, so that's one way to do it, to do the determinant. But you will notice that while all our problems are going to have both the omega and the alpha along the k direction, okay? So there's going to be a couple of zeros here. And then the thing that they're cross multiplying or like taking the cross products of are going to be in the I and j direction and have no k, because we are only considering 2D problems. Because we are considering only motion in the plane, the angular velocity is always perpendicular to the plane, and the velocities themselves are going to be in the plane ij. So alternatively, so this is an alternative to doing the cross, well, this determinant. So this is, I guess, the determinant, right? So this is the determinant. Alternative to the determinant is basically remember the following things. I cross j is k, j cross k equals I, and k cross I equals j. So if that makes sense. So if you say, I like to remember it like this. If you say I don't know, in some direction, write it. Basically, if you have the sequence I, j, k or something, and you have this loop, basically. If you do I cross j, you get k, k cross I, you get j, and so on. So if you do it in the cyclic manner, you basically get the next one over. And then if you reverse this, j cross I is minus k, k cross j is minus I, and I cross k is minus j, okay? So if you reverse this, you get the negative sign. If you're not going the cyclic order, you get a negative sign. And if you remember these things, well, which really depends on like whether you're going cyclic or anti-cyclic, like j cross I is sort of going backwards and you get a minus k there. If you know that, then you can quickly do these cross products. Well, it's basically equivalent to the determinant, but you can say, let me just do that now. 5k cross, what was it? 3i plus 2j is basically 5 times 3 is 15. And then we have k cross I. K cross I is sort of in the correct cyclic order. You go ijk, I. So this is basically going to be a j. And then you go plus 10 k cross j. So this is basically 15 j. And then k cross j is kind of this opposite, sort of backwards. So it's a minus I. Okay, so that's basically the same thing that we got here, 15j minus 10i, 15j minus 10i. Okay, any questions? I guess we'll stop there, and I guess we'll see you next time.